Example here, and it's an example which is actually exploring the concepts of injectiveness, surjectiveness, and bijectiveness. And we've been asked to consider a particular function. Now, the first thing is we need to break down what the notation actually says. And what we have here is we've actually got the first part of the function, which is defining what the domain is. And we have to write that down. So straight away, we know that the domain, now don't forget, the domain is the input numbers, the only input numbers you are allowed to actually choose. So from this notation, we're told that the smallest input number for x is 1, and then we can choose any decimal we like, going on forever. Simple as. Now we're looking at the next part of this function, which is this bit here. And what we've seen before is we know that this is called the codomain, which is going to be the output numbers, which is the f of x numbers or the y numbers. And we're told that the codomain is equal to the lowest number in the codomain is a 2, and it goes on every decimal forever, doesn't stop. Then we now know that the function itself brings x, the input number, and turns it into x squared minus 2x plus 3. And traditionally, we write that as f of x is equal to x squared minus 2x plus 3. And we've seen in other parts of the course where we'd actually introduce what we call the empty bracket formula, which we don't need to do today. Now, we want to complete the square. So we need to remember what the completing the square format is. And the completing the square format is a on x minus h all squared plus k. We also know by inspection that the a will be the number in front of the x squared. So we're now going to pick off very quickly that a is equal to 1, and we'll be using that later on in the problem. Well, we'll be using it straight away, to be honest, because the first thing we're going to do now is we're going to put a 1 in front of that bracket. Now, the technique, as we've seen before, is to expand the brackets. Now, I'm not going to show the working out for that. I'm just going to expand it. So it's going to be 1 on x squared minus 2hx plus h squared plus k. So we finally end up with a tidy up version, which is going to be 1 on x squared is x squared, 1 on minus 2h, which is going to be minus 2hx, plus h squared plus k. So the completing square format, probably worth about 10 marks in the exam, is relatively quick and easy to do. And then what we do is we bring down the original equation, which was x squared minus 2x plus 3, and we do the comparison. So we do the comparison, and the comparison is we compare the x components, and we spot that minus 2h will be equal to minus 2. So we've now got minus 2h is equal to minus 2. We can change the signs on both sides, and we can divide both sides by 2, and we get h is equal to 1. Now we do the comparison for the constant, and when we do the comparison for the constant is this number here, which equates with the number 3 written on the line below. So we've now got h squared plus k is going to be equal to h squared plus k is going to be equal to plus 3. So h squared plus k is going to be equal to plus 3. Now we know h is 1, so we've got 1 squared plus k is equal to 3. So we've got 1 plus k is equal to 3, and therefore k clearly is equal to 2. So you've got k is equal to 2, and then what we're going to do now is we're going to go back to the completing the square format, which is f of x is equal to a on x minus h all squared plus k. So we've now got f of x is equal to 1 on x minus 1 to be squared plus 2. We know that this is a happy quadratic, so we can draw the quadratic looking happy. We know that the vertex is given by the coordinate, which is h, comma k, and we know that this vertex is 1, comma 2, because we just worked out what h and k actually is. And we don't need it for this question, but it's a very, very useful focus. We know that the axis of symmetry is going to be x equals 1. We know that the minimum value is going to be y is equal to 2. And I'm going to explain why that is important in the next few minutes. Okay, you can pause the video at this point and see if you can recreate to this particular part of the problem. Now, this is where people go wrong, because we were told very early on in the problem quite clearly that the lowest value of x that we were allowed to use is given by this line here. The lowest value of x is 1. We're not allowed to use anything less than 1. So this value here is where x is 1. That means we're not allowed to use any numbers here on the left, because all the x values to the left of 1, we've been told, are not part of the domain. So what we've got to do now is we've just found out that this part of the graph actually doesn't exist from this definition up here. The domain of definition, the smallest value of x is 1, which means this part of the graph actually doesn't exist. So I'm going to leave it there as a dotted line. And that's what you've got to learn. That it's what was the smallest value of x. If I was plotting this graph, what is the smallest value of x I can put in? 1. Can I put 0 in? Not allowed. And so therefore, what's the first dot? What's the first plot? If I was plotting this back in 3rd year, this would be the very first plot I would be allowed to do. And then I would be doing the other plots on the left. And when I finish plotting it, I would then, using the domain of definition, I would then draw my graph, and the rest of this would never be drawn and would not exist. So at this moment in time, this is the sketch. So let's start answering some of the questions. Part A. Is this a function? And the answer is yes. And why is this a function? Because it passes the vertical line test, which we've discussed in class. Is this function injective? Well, the answer is yes. Why is this function injective? Because it doesn't have a turning point. Now, we know quadratics have turning points, but only if it's a full quadratic. What have we just done? We've just rubbed out half the quadratic. And because we've rubbed out half the quadratic, it's now purely an increasing function. And if it's purely an increasing function, it's injective. So it's yes, and the answer is why. because it's increasing, always increasing. So don't forget the definition, always increasing or always decreasing, i.e. no turning points. And you could have said that, no turning points. Is the function surjective? Well, you don't know, quite possibly. So what do you fall back on in mathematics? If you don't know something, if you're not sure about something, fall back on a formula, fall back on a definition, and you're going to get method marks. So the question here is, not sure. So what is surjectivity? Surjectivity is when the range is equal to the codomain. So we know that the definition of surjectivity is range is equal to codomain. Now, fall back on definitions, gentlemen and ladies. Is range is the lowest value on the y-axis to the highest value on the y-axis. So take a long, hard look at your graph. And this is the lowest point. And what is the y value at this lowest point? The y value at this lowest point is y is equal to 2. And this graph goes on forever. So what's the highest value because this graph goes on forever? Well, we can't say equals infinity. We can say travels to infinity. So therefore, we now know from the picture, from the sketch, that the range definitely has a value of 2, hence the square bracket, and it carries on forever, so it's travelling towards infinity. Now let's go back to the problem. What did they say the codomain was, which is the reason why it's always worth writing it down? They told you that in the problem that the codomain was equal to 2 to infinity. So, what can we now say about surjectivity? The answer is yes. And that's how straightforward it is. And it's purely based on looking at the information given to you in the question, looking at your graph, knowing the definitions. If you don't know the definitions, you can't do it. Okay, so is this function bijective? Fall back on your definition. What do we know about a bijective function? Well, a bijective function is a function which is both injective. Bijective is injective and surjective. So do we have 2 yeses? Yes, we do. So therefore, yes. And if they ask you to give a reason, then you just basically point back to your definition, because bijective is where you have the function is injective and surjective. Another 5 marks. So now we're moving on. Find, if it exists, the inverse of this function. Well, what's the condition? What's the only necessary condition for a function to have an inverse? Is it must be bijective. So we know there is a inverse to this function. So if we want to get 3 marks out of 10 or 2 marks out of 5, we can just say there definitely is an inverse because it is bijective. So we know we've got that. That's great news. Now, at this stage, in order to make space, I'm going to rub out what's up on the screen, and then I'm going to continue with part E. And part E is the part where it says, okay, you've established that there is an inverse. It definitely does have the inverse because you've established it's a bijective function. So you now want to actually find out what that inverse is. So to work out the inverse of something, you write the function in terms of y. So y is equal to x minus 1 all to be squared plus 2. I'm going to write it the other way round. You'll see why in a minute. Now, before I start working through this, I'm going to explain to you what it means to have an inverse function. So at this moment in time, we've got this graph. It's at 1 along and it's at 2 up. So this is where the graph starts, and it's a quadratic form, so it carries on like this. And what we've got here is we're given a value of x, and that value of x will generate a value of y. So what we have here is if we want to use the function, each value of x will generate one and only one value of y, which makes it injective. And what does an inverse function do? An inverse function basically allows you to travel from the y back to where you started. That's what an inverse function does. It allows you to go back along the route and travel down. Now, if the original function was y equals, then the inverse function must be, because it's going the other way, must be x equals by pure logic. So to find an inverse function, all you've got to do is to find x. So I'll say that again. What did the original function do? It takes you from an x value on the x-axis, and it takes you up to the curve, and it gives you a y value. What does an inverse function do? It starts off on the y-axis, goes to the curve, and gives you an x value. So to get an inverse function, you need to get a function which says x equals, because you're looking for the x. So you might want to, well, you can rote learn that, but if you've got some understanding from what I've just said, then all well and good. So what we're going to do now is we're going to quickly find the x. So what we're going to do now is, bring the 2 over, and it becomes a minus 2. We're going to square root both sides. But when we square root, the answer is plus minus. Come back to that in a minute. And then we bring the 1 over, and that 1 becomes a plus 1. And then we have to decide, is it a plus answer or is it a minus answer? Because it's on the right-hand side, it means it's a plus. If the quadratic had been drawn on the left-hand side, it would be the minus version. So we've now got x is the square root of a plus square root of y minus 1 plus 1. So we've now got the function of y is equal to the square root of y minus 1 plus 1, and then we change, would you believe, the y into an x, and, it's an inverse function, so we call it f minus 1, and that becomes x minus 1 plus 1.